Hello everyone. Today I will be presenting my final project for ADTA 5550, where I explored convolutional neural network performance using TensorFlow. Specifically, I built, trained, and tested CNN models on two different datasets, the MNIST and CIFAR-10, to understand how dataset complexity impacts model architecture requirements and accuracy. This project demonstrates that matching model complexity to data complexity is crucial for achieving optimal performance in deep learning applications. So let's dive in. Let me give you a quick overview of what we'll cover today. First, I'll introduce both datasets we worked with, the simpler minced digit dataset and the more complex CIFAR-10 image dataset. Then I'll walk you through the initial CNN model design that was applied to both datasets. We'll examine the performance comparison between the two models, which revealed some interesting challenges. Based on those findings, I designed an improved model specifically for CIFAR-10, and we'll look at those results. Finally, I'll share key conclusions about the relationship between data complexity and model architecture. The first step of the project was to download an additional dataset which contained images or audio files. From Kaggle.com, I found a dataset which includes images of cloud segmentation in satellite images. The dataset includes a total of 78,880 total images, with 8,400 patches for training and 9,201 patches for testing. Each of the patches includes 4 corresponding spectral channels, which include red, blue, green, and near-infrared colors. Once we review the additional datasets and models, we'll come back to this dataset later in the presentation. To begin the project itself, the first step was downloading the CIFAR-10 dataset, and it was saved to a newly created folder and subfolder in my Google Drive so that the data could be easily pulled into the Google Colab notebook that we were utilizing for this project. Let's start by looking at the CIFAR-10 dataset. This dataset contains 60,000 color images across 10 different classes of everyday objects, which include airplanes, automobiles, birds, cats, deer, dogs, frogs, horses, ships, and trucks. It's a mouthful. Each image is 32 by 32 pixels with 3 color channels, red, green, and blue. As you can see from these examples, CIFAR-10 images are very complex. The objects appear at differing angles, scales, and positions. There's also background clutter, varying lighting conditions, and natural variations within each of the different classes. For instance, not all cars look the same, and not all birds have the same coloring or pose within the images. Now let me walk you through the initial CNN architecture that was designed. This same structure was applied to both data sets, both the MNIST and the CIFAR-10 data, initially to establish a baseline comparison. The model itself begins with the input layer, which is 32 by 32 by 3 for CIFAR-10, representing the width, height, and the RGB channels. We start with the first convolutional layer, which applies 32 filters with a 5 by 5 kernel size, using same padding and ReLU activation. This produces feature maps of 28 by 28 by 32. The first max pooling layer then reduces spatial dimensions by half using a 2x2 filter with stride 2, resulting in 14 by 14 by 32. Now the second convolutional layer increases the depth to 64 filters, again using 5x5 kernels with same padding and ReLU activation, maintaining the 14 by 14 spatial dimensions. The second max pooling layer will further reduce the images to 7 by 7 by 64. Next, we flatten these feature maps into a one-dimensional vector of 3,136 values. This feeds into a fully connected layer with 10,024 neurons using ReLU activation. We then apply dropout at a 50% to prevent overfitting by randomly deactivating half of the neurons during the training. And finally, the output layer contains 10 neurons, one for each class, producing logits that are converted to probabilities using softmax. The loss is calculated by using softmax cross entropy. The model was then trained for 5,000 steps with batches of 100 images each. During each training step, the model performs forward propagation, passing images through all layers to generate predictions. The loss function then calculates how far off these predictions are from the true labels. Using this loss value, backpropagation computes gradients that indicate how to adjust the weights and biases. The optimizer, in this case we used Atom, updates these parameters to minimize the loss. This process will repeat for 5,000 steps, with the model gradually learning to extract relevant features and make more accurate predictions. We evaluate the accuracy every 100 steps on the test set to monitor the performance without using test data for training. Now, let's examine the results of the testing. The model started with 54.75% accuracy, which when you think about it is barely better than randomly guessing for 10 classes would give you. The model did, however, improve to 61.16% accuracy. However, the progress during this time was extremely slow. The model continued learning throughout the training, reaching a peak of 69.6% before finishing at 68.43% accuracy at the final step of 5,000. Comparing our results from the MNIST dataset to those of CIFAR-10 dataset, starting with MNIST, the performance here was excellent. The model achieved an initial accuracy of 94.84% after just 100 steps. By step 500, the accuracy had climbed to 97.8%, and it continued improving steadily throughout the training. The model was able to reach peak performance around step 4,200 with 99.18% accuracy and finished training at step 5,000 with 98.97% accuracy. The slight fluctuations near the end of the model's training, they're normal and represent the model fine-tuning on different test batches. This accuracy and high level of accuracy demonstrates that our same two-layer CNN architecture used with the CIFAR-10 dataset was pretty well suited for the MNIST dataset. the model was able to successfully learn to distinguish between handwritten digits with minimal errors. The relatively simple features needed for the image detection, the curves, the lines, and the basic shapes, those were adequately captured by just 2 convolutional layers. This 68.43% final accuracy for the CIFAR-10 dataset is significantly lower than the MNIST at 98.97%. While it's better than a random chance, it's far from the performance we would want in a practical application. So the model was clearly having difficulty distinguishing between the complex, varied images that are found in the CIFAR-10 dataset. So why such a dramatic difference in the performance? Let's break it down and look at the key factors. First, image complexity. The MNIST images are grayscale with simple geometric shapes, while the CIFAR-10 images contain a complex color pattern, texture, and often intricate details requiring much deeper feature extraction. Second, intra-class variability. All MNIST 5s look relatively similar, but in CIFAR-10, dogs can be different breeds, different colors, different sizes, and can even be sitting in different poses. This variability requires the model to learn abstract, generalizable features. The third reason is the background and context. The MNIST digits are isolated on plain backgrounds, whereas the CIFAR-10 objects appear to have varied contexts with different backgrounds, occlusions, and lighting conditions. The fundamental insight here is that our 2-layer CNN, while it was sufficient for the MNIST, is simply too shallow to capture the varied complexity of CIFAR-10 images. The model, therefore, is underfitting. It lacks the capacity to learn the rich feature representations which are needed for accurate classification. Simple digit recognition needs only basic edge and curve detection, whereas the real-world object classifications found in the CIFAR-10 data requires a hierarchical feature learning from edges to textures to object parts to complete objects. Based on this analysis, I then designed an improved model specifically for CIFAR-10. Let's take a look at some of the key modifications to try to address the underfitting problem by increasing the model capacity and feature extraction capability. First, I added a third convolutional and pooling layer. This creates a much deeper network that can learn more hierarchical features, from the simple edges in the earlier layers to more complex object patterns and parts in the deeper layers. Second, I increased the number of filters progressively. We utilized 64 in the first layer, 128 in the second, and 256 in the third. This allows the model to capture increasingly complex patterns at each level of the program. The third thing that I did, I reduced the kernel size from 5 by 5 to 3 by 3. Using smaller kernels is more computationally efficient and have been shown to be more effective in modern architectures. They allow the network to build complex features through multiple layers rather than trying to capture everything in larger filters. Based on this analysis, I designed an improved model specifically. So let's take a look at that. Let me walk you through the updated architecture in a little bit more detail. The input remains 32 by 32 by 3. The first convolutional layer now uses 64 filters with a 3 by 3 kernels, which produces 32 by 32 by 64 feature maps. Max pooling reduces this to 16 by 16 by 64. The second convolutional layer uses 128 filters, maintaining the 16 by 16 spatial dimensions, but increases depth to 128 channels. Max pooling reduces to 8 by 8 by 128. The new third convolutional layer applies 256 filters, producing 8 by 8 by 256 feature maps. And a final pooling reduces to 4 by 4 by 256. After flattening to 4,096 values, we use a fully connected layer with 512 neurons, which are optimized for the increased feature representation. We continued to maintain 50% dropout, and the output layer still has 10 neurons, which represents our 10 classes of images. This deeper architecture with more filters provides the capacity needed to learn complex features, while the smaller kernels maintain computational efficiency for the computer in our model. Now let's take a look at how this improved our model performance. The results clearly demonstrate the value of appropriate architecture design. The model started at a 43.40% accuracy. However, as training progressed, by step 1000, the accuracy had reached 61.85%, which was already catching up to the original model. By step 2000, it hit a 70.1% accuracy rate, which surpassed our original model's final performance. The model then continued improving steadily, reaching 74.16% at step 4200, and ultimately finished at 74.11% accuracy. One aspect we should consider in the computational trade-offs in architecture design. While the second model started at 43.40% accuracy, which was actually lower than the original model's 51.97%, we might think that this is concerning, but actually it's pretty expected. The deeper network has more parameters to learn, so it ultimately takes longer to find good initial patterns. The model continued improving steadily, reaching a final accuracy of 74.11%. That's a 5.68% point improvement over the original model, a relative improvement of nearly 8.5%. The accuracy in the second model is smoother and more stable in later training compared to the original model. This indicates the deeper network is learning more robust, generalizable features rather than just memorizing training data or getting stuck in local patterns. The final accuracy of 74.11% demonstrates that proper architectural design, which is able to match the model complexity to the data complexity, significantly improves our performance. Our improved model has significantly more parameters than the original model. The third convolutional layer alone adds thousands of learnable parameters, and the expanded fully connected layer increases the memory requirements. Now let's talk a little bit about the training time. The improved model took noticeably longer to train per step. Wish I would have known that before I started running it, but that's okay. We learned through the process. And approximately 40% more time was used in the second model due to the increased computations, which, thinking back on it, makes sense. For 5,000 steps, this added at least double the time than it took me to run the original model. Additionally, if we look at the memory requirements, the 4,096 neurons fully connected layer requires substantially more memory than the original 1,024 neuron layer. This could be limiting on resource-constrained devices. And finally, the inference speed. The more parameters mean the slower predictions at deployment time. Now, this wasn't a problem for this particular project. However, for real-time applications, this matters and should be something that we think about. However, these costs should be weighed against the 6-point accuracy improvement. In many applications that we've discussed throughout this course, medical diagnosis, autonomous vehicles, security systems, higher accuracy will justify the need for increased computational cost. The key is making informed trade-offs based on application requirements. Let's put all three models side by side now to compare the complete picture of what we've run. The MNIST model achieved 98.97% accuracy with just 2 convolutional layers, which was clearly sufficient for the task at hand. The original CIFAR-10 model, using the same architecture as the MNIST, managed only 68.43%, which demonstrates that there was severe underfitting in the model, while the improved CIFAR-10 model reached 74.11% accuracy, which was a pretty good improvement, but still well below the MNIST levels. This comparison reveals several important insights to our project. First, the 30-point accuracy gap between the MNIST and the improved CIFAR-10 model shouldn't be considered a failure. It simply reflects the fundamental difference in the task difficulty. The MNIST is an inherently easier problem to solve, given the nature of the data set and the less complex images that it holds. Second, the 5.68-point improvement from the original to the improved CIFAR-10 model shows that architecture matters tremendously. The same dataset with better designed model yields significantly better results. There's clearly room for improvement, however, in our CIFAR-10 model. Our improved model represents a solid foundation, but is not the ceiling of the performance, and there are many additional things that we can do to improve upon the accuracy. The principles demonstrated in this project extend far beyond the specific data sets that we used. Understanding how to match model architecture to data complexity is crucial across many real-world applications. So now we'll come back to those satellite images that I discussed at the beginning of the presentation. So when we look at the satellite imagery analysis, the cloud segmentation data set that I initially explored uses similar principles. It has images which are complex, with varied imagery requiring appropriately deep architectures. The higher spatial and spectral complexity and the pixel level labeling along with a richer information content, all means that we would need to build a much deeper model, more capable, often with an encoder-decoder structure, which is typically sufficient for CIFAR-10. The cloud detection is a semantic segmentation problem. When we think about it, every pixel in the image must be labeled, whether it's a cloud or not a cloud. This means we would likely need almost twice the number of convolutional and pooling layers than we used in the CIFAR-10 dataset, which was required. When I first started the project and was looking for datasets, I didn't quite understand that concept of why it was important, the images that we were looking at. But certainly after taking a look and comparing our three models to each other, it now becomes clear why how you build your model is so important to the images that you're reviewing to ensure for accurate and proper classification. Based on this project, I can share several practical principles for the CNN architecture design. First, we have to start with understanding our data complexity, like we were just talking about. Simple, constrained data like the MNIST needs simpler models, whereas complex, varied data like CIFAR-10 needs much deeper models with more parameters in place. You should always examine your dataset characteristics before choosing the architecture because it will definitely have an impact on your final product. Second, we use progressive feature depth. Increasing filters from 64 to 128 to 256 in the improved model allowed for earlier layers to detect simple features like the edges of the images, while deeper layers combined these into complex patterns. This hierarchical learning is fundamental to the success of your CNN. Third, smaller kernels in deeper networks often are able to outperform larger kernels in shallow networks. The 3x3 kernels in our improved model were more efficient than 5x5 kernels in the original, while being computationally cheaper. Fourth, we need to monitor both training and test performance. If testing accuracy plateaus well below training accuracy, then we're overfitting. We need to add regularization. If both are poor, we're underfitting, and we need to increase capacity. Our original CIFAR-10 model showed underfitting, so we added capacity rather than regularization. Fifth, and this one's important, and I learned it the hard way, we have to be patient with deeper models. The improved CIFAR-10 model started with a lower accuracy than the original, but it eventually did surpass it with sufficient training. Deeper networks need more time to converge. And let me tell you, I was waiting on that to get to the final step. It took a while, but I learned it is important to give it the time that it needs. So a key principle of deep learning, the complexity of the model really does need to match the complexity of the data set to achieve optimal results. So now that we're at the end, let me conclude with the main takeaways that I got out of this project. First, we successfully built, trained, and tested CNN models using TensorFlow directly, gaining deep understanding of how convolutional neural networks function at a fundamental level. Second, we demonstrated that the same CNN architecture performs dramatically different on datasets of varying complexity. MNIST's simplicity allowed for a 99% accuracy with just 2 convolutional layers, while CIFAR-10's complexity yielded only 68% accuracy with an identical structure. Third, we identified underfitting in the original CIFAR-10 model and systematically addressed it through a deeper architecture with more filters, smaller kernels, and additional layers, achieving a 74% accuracy, which is a meaningful improvement over the original model. Fourth, we validated a fundamental principle of deep learning. Model complexity, once again, must match data complexity. If it's too simple, the model underfits. Appropriately complex, and performance improves significantly. Finally, we learned that effective deep learning isn't just about applying algorithms. It does require careful analysis, principled design decisions, definitely iterative improvement, and an understanding of the relationships between data characteristics and model architecture. These lessons extend far beyond this specific project to any machine learning application we might encounter in our future careers. Thank you so much for your time. I hope you've enjoyed this presentation.